Good day, Iman. Welcome to today's physical science lesson. I hope you're doing well. We're going to be going over some more exam revision from Module 1 on matter and materials, and we're going to be going over questions 8 and 15. I'm not doing so good. My brain's a bit foggy. I'm still recovering from side effects of being vaccinated, but luckily we have a system for doing these problems, so I don't have to think too hard. I can let the system do the heavy lifting. Question 8.1 asks, explain why metals can easily be molded, are malleable or ductile. The answer to this question goes back to the theory on metallic bonding. If you remember, metallic bonding is where we have these positive nuclei surrounded by this sea of delocalized electrons. Pictorially, it would look something like this, where we have two positive nuclei, and there's this sea of electrons floating around. Now, this leads to two properties for metals. Firstly, metals can conduct electricity because these electrons are free to move. Secondly, metals can be bent. Now, we could move this nucleus on the right-hand side a little bit down, say over here, and it would still be surrounded by this sea of electrons holding everything together by the electrostatic forces of attraction. Question 8.2 asks, due to which property of nonmetals is oxygen a gas at room temperature? The textbook answers this very simply. They say the nonmetals have a low boiling point, which means they evaporate at low temperatures. We could also look at the intermolecular forces between the oxygen molecules. I've just drawn two of them over here. These are weak van der Waals forces of attraction. Just double check the theory on that in your textbook. Question 8.3 asks, how does the electrical conductivity of metals and metalloids change with an increase in temperature? We've already seen with the metals, when we increase the temperature, the conductivity decreases. And that's because the increase in temperature makes more vibrations, more movements within the metal, and there's a greater chance of electrons colliding. So that would lower the conductivity. For metalloids, the opposite is the case. When we increase the temperature, the conductivity actually also increases. Question 8.4.1, describe a simple experiment to compare thermal conductivity of substances. This is really simple. We could take a substance, hook it up to a heat source on the one side, for example, put it underneath a candle, and then have a substance which melts easily like wax on the other side. So if we heat up the one side and the material is a good conductor, then the heat will pass through and melt the beeswax quickly on the other side. If it's a poor conductor, it would take longer to melt. Question 8.4.2, describe a simple experiment to compare the electrical conductivity of substances. Once again, this is really simple. We could have an electric circuit with a light bulb and have our substance as part of the circuit. So if it's a good conductor of electricity, the light bulb will shine brightly. If it's a poor conductor, the light bulb will be more dim. Question 8.5, give an explanation for each of the following facts. 8.5.1, it is better to use a wooden spoon than a metal one when making fudge or sweets on the stove. So this is really simple. If we have a metal spoon, the metal will conduct the heat from the stove and eventually burn your hand. A wooden spoon is a poor conductor of electricity, heat, so this won't happen. Question 8.5.2, also giving an explanation of why toilet seats are always cold, even when the temperature in the room is warm. And this once again goes back to heat conductivity. Plastic is a poor conductor of heat, so it won't take on the temperature of the surrounding environment. If the room is warm, the seat will still stay cold. Question 8.5.3 is a similar story. It asks us to explain why you can put your hands into a very hot oven for a few seconds to remove a hot dish from the oven without getting burnt, but if you touch the dish or the hot plate for just a fraction of a second, you will get burnt. And this once again goes to heat conductivity. If you're just putting your hands into the oven, the air is a very poor conductor of heat, so you won't get burnt. But if you touch the dish is a conductor of heat, so you do get burnt. Question 8.6. For each of the following materials, say which special properties of the materials are utilized for the specific function. We have cotton clothes, carbon electrodes, plastic cups, and steel gates. This is pretty straightforward. You can check the answers in your textbook. Cotton clothes, for example, cotton is a poor conductor of heat, so cotton would be good for making winter clothes or summer clothes. Carbon is a good conductor of electricity, so it would be good for making electrodes. Question 15 looks at Aufbau diagrams, and they're looking at the specific element phosphorus. If you check on the periodic table, phosphorus has the letter P, it's in group 5, and has an atomic number of 15. That means it's got 15 electrons or protons. Now, when we draw the Aufbau diagram, we just have to remember to label our energy levels and the orbitals for each energy level. For energy level 1, we just have one s orbital. For energy level 2, we have an s orbital and 3 p orbitals. Energy level 3 has an s orbital, 3 p orbitals, and 5 d orbitals. I haven't drawn in the 5 d orbitals because there's no need to. Currently, there's enough space for all 15 electrons. And I filled in the electrons level by level. The only notable thing is that in this last line for the 3 p orbitals, I filled in the electrons one by one. And this follows Hund's rule, which says we need to fill in the electrons one by one if it's the same type of orbital until we get to the end. And if there are more electrons available, then we can put a second one in. Question 15.1.2, which rule did you apply for the filling of the outer sub-energy levels with electrons? Give the rule in words. So this is just a definition of Hund's rule, which I explained in the previous question. Just double check the textbook for the full definition. Question 15.1.3, if an atom is ionized, how many fully filled energy levels will a phosphorus ion have? A phosphorus ion would be the phosphorus atom having gained 3 electrons. You can double check this in the table in your textbook. And what this means is that it gains a charge of -3 and it has 3 full energy levels. Question 15.1.4, give the SP notation of an ion of the element mentioned in the previous question, so the phosphorus ion. Basically, we just have to do SP notation of this. SP notation is just shorthand notation for the Aufbau diagram, and it goes like this. 1s has 2 electrons, 2s has 2 electrons, 2p 6 electrons, 3s has 2 electrons, and 3p, having gained those 3 electrons, now also has 6. Question 15.2. Consider the electron configuration of the elements P, Q, and R. For each of the elements, say if it's more likely to form a cation or an anion during ion formation. Next to it, also indicate the valency of an atom of this element. Just to refresh, a cation is a positive ion where the element has lost electrons, and an anion is a negative ion where it's gained electrons. An easy way for me to remember is anion, onion. Onions make me cry and are associated with negativity. Now on to the question of whether these elements gain or lose electrons when becoming ions. When becoming an ion, an element achieves a full energy level state, a state of most stability. If we go back to our phosphorus example, the first two energy levels are full and the third energy level is incomplete. Phosphorus can either gain 3 electrons, so now it has 3 full energy levels, or it could have lost these 5 electrons and just have 2 full energy levels. Now it's easier for the phosphorus element to gain these 3 electrons than to lose the 5 electrons, so that's why our phosphorus ion is -3. Element P has the electron configuration 1s2, 2s2, 2p to the 5. I've rewritten it here and I've drawn the alpha diagram which corresponds to it. So we can see that we've got the first energy level full and the second energy level has 7 electrons, one short of reaching the stable state. In becoming an ion, this element could either lose all 7 electrons to have just 1 full energy level, or it could gain a single electron to have 2 energy levels full. In this case, it would be easier for this element to gain an electron than to lose all 7. So we'll add in an electron in the last slot, and our electron configuration will now be 1s2, 2s2, 2p to the 6. The valency of this element is the number of electrons in the last energy level, and in this case it would be the 7. For element Q, we can see that the first 2 energy levels are full and the third energy level is incomplete. 3s1, 3p1 means there are 3 electrons in the third energy level, so it has a valency of 3. And in achieving stability, in becoming an ion, it could either gain 5 electrons, so that the third energy level is full, or it could lose those 3 electrons to have just 2 full energy levels. In this case, it would be easier to lose the 3 electrons than to try gaining 5. So the ion would be +3 in this case after it's lost the 3 electrons. Element R follows a similar story. The first 2 energy levels are full. The third energy level has 6 electrons. So ideally it would like to gain 2 electrons to have 3 full energy levels. And the ion for this element would be -2 after it's gained those 2 electrons. And that concludes today's video lesson. I hope you understood. Please let me know if you didn't, so we can catch it in time before the exam. Thanks and take care.